Okay, guys. Everybody got the homework number 3. It's just a simple exercise. You can refresh your mind solving some of the materials. Okay, let's continue on this thing first. We were discussing about this Newsband model, and in previous class we've derived that this. As we discussed before, this CS means cost of shortage, cost of leftover, over cost of shortage. That's the GQ star. What is G? Is a cumulative distribution function. So this is not exactly the cost value itself. It's a probability, cumulative probability. So based on this, you have to derive the actual Q star value, like this. Okay, let's do some example. Here, this is a perfect example of Newsband model application. Let's say you are the seller of Christmas lights. You decorate those blinking small light bulb lights on top of the Christmas tree. And those sales peaked just before the Christmas days, but after the Christmas day, nobody will purchase that. So Newsband model is the perfect model for those kinds of problems. So example. Example. Christmas light. Okay, that's the product. In order to apply this Christmas model, we got to know the COCS, right? So first one first. Set of light, because it's a set. You have many light bulbs, so you're gonna sell it set by set. Cost is $1 to make and distribute. But you sell it $2 because you got to have some margins, right? Okay, the other thing. So, can you guess what would be the cost of the overage or shortage based on that? This is not enough information, so one more information is like this. Any set not sold by Christmas Day will be discounted to half. Okay. Based on this information, let's deduce the CO and CS. Okay. Anyone? What is CO? It's a cost of overage. Alright? If your demand is exactly same as the sales, if your demand is exactly as your order amount, then there will be no such thing. But however, look at this. It's a $1. So you got to pay $1 to bring the product to your inventory. And you sell those product at $2. $1 is your margin. But what if you cannot sell? Then those one will be discounted by this one. So it's a big discount, 25% of the original price. At the market, it's a $2 before the Christmas, but after the Christmas, now it's a 25 cents. 50 cents. So it's a 75% sale. However, based on this information, you can calculate that it is 1 minus Can you guess? Does that make sense? You purchase it $1, but you sell it 50 cents. You lose 50 cents whenever you sell it. It's a cost of overage, right? Is it clear? What if, even though it's after Christmas, you still sell it at $1? What's the cost of overage? 0, because you purchase it at $1 and you sell it $1, so no cost at all, right? Okay. So 1 minus this is the cost of overage, right? Okay, then what would be the cost of shortage then? $2? Why is that? Selling cost is, when we talk about shortage, it's before the Christmas, right? The demand is larger than your actual inventory size. So, what do you earn by selling 1 unit before the Christmas? How much do you earn? $1. It's the profit from one sale. Cost of shortage is lost sale. So it's going to be $1. This is selling cost minus purchasing cost. Okay. Based on these two information, we can calculate this. CS, CO plus CS. This is 1 over 1 plus 0.5. It's about 0.666 or 0.67. What's that value? Is it cost or what? This is a cumulative probability at the value of the CDF. Okay? We don't know yet. However, if this is all about that demand is a random variable which follows some specific, statistical distribution, and every statistical distribution will have CDF, which is a constantly increasing function. Whatever it is, this means at the top it's a 1.0, right? Now we know this information. Okay. Then we have to guess that one, right? Since this is a CDF, this is constantly increasing and continuous function, so when you choose one value on the y-axis, there is only one unique x-axis value. Okay, that's mathematically true, so we can get this value if we know the function itself. So let's make our example more simpler. So let's assume it's our unknown random variable demand is following normal distribution Okay. Then, based on this one, from this, we can continue to this. Okay, let me explain a little bit later. Sorry, something's wrong. Right? You know, in all the mathematics book, if you browse through some of the appendix, then you will clearly find the table of statistical distribution, right? Do you know how to read that table? Okay. Those tables are just pre-calculated function of normalized normal distribution. So if you know this function value, you can search that value from the table and you can calculate those values. And from a normal distribution table, this is 0.44 if you look through the table, and which means this is G value, and we know those Q star is right, and we know this is Z. Okay. Okay. We still cannot calculate Q star with this information only. Okay. let's re-summarize it. We are the Christmas tree vendor, and we'd like to sell the Christmas tree, and this is the information, cost of overage and cost of shortage. And all we wanted to do is minimize the cost based on a random demand. Okay, in order to complete this model, we first have to know the forecast of the demand. What would be the mean and standard deviation? We assume that our demand is random, however, it follows normal distribution. But we haven't specified anything yet. In mathematics, to define a normal distribution, we have to define two parameters. One is the mean value, and one is the standard deviation. Without these two values, you cannot draw the normal distribution curve. It's too general, right? So, in forecast, demand forecast, we have to specify this and this value here, right? And we can use those exact value here and calculate the optimal inventory size. Okay, let's say we are the Christmas tree light vendor, and our purchasing cost and distribution cost is $1, and we are selling at $2, but after the due date, it's gonna be $0.50, and our random demand are forecasted to follow a normal distribution of mean value of 10,000 units and standard deviation of 1,000. Let's assume that. It's not discrete, but at least we can guess the demand will be something like that. Then what would be the optimal inventory size? If we plug those information to that, then with this information, it is optimal to order 10,440 units. It's a little over of the average value. So the probability of overage will be a little bit higher than probability of shortage. However, that's because of the cost of overage is half of the cost of shortage. If these two values are exchanged, then the optimal inventory size will be less than the average of the forecasted value, expected value. Okay, any question? Yep.
What is G mean? G is just probability.
G is CDF probability. In the definition, we defined this Gx like this is demand.
Oh, sorry, G, not G, G.
What G? Ah, Z. Z. Sorry. Okay, let's make a problem simpler. Think of normal distribution with zero mean and unit standard deviation. If we draw that normal distribution graph, it will look like something like this. Okay? And if you browse some mathematics book, you can actually see the exact function, the formula, right? And whenever you plug some x-axis value, you can easily calculate the y-axis value, right? Okay, what's the meaning of those kind of thing? This is the mean and 1 sigma, 2 sigma, 3 sigma, and vice versa here. This is the probability. Y-axis means probability. Right? To be more exact, it's a probability density, because we call this a PDF, probability density function, probability distribution function. Okay, density function. So it's a the density means if we, let's say this is some fx, fx this is probability, right? Okay. Let's say 10,000 of the mean value and 1,000 value of standard deviation. That's what we expected value of our random demand. Okay, what would be the probability of having exactly 10,000 demand? In order to answer it, well, we can draw this normal distribution, and well, if the value x is at the mean value, we can read those probability, right? What would be the value probability? The demand turns out to be 10,500 or something. Then we can read, sorry, no, forget about this. Based on that, we can, well, the probability is something like that. What's the probability of we have millions of demand? Well, you still have a probability, but the probability is really, really small at the time, because it's a two way over the mean expected value and standard deviation. Okay, we can deduce the probability of having some exact demand with this PDF, right? Any questions so far? And if we integrate it, this function will be something like that. At this value, it's a 1.0. What we did is we integrated. What? CDF, right. This normal, so we should draw it from minus infinity to plus infinity, because this function actually stretches to minus infinity to plus infinity. But anyway, at some value, let's say this is g, and let's say this is 0.67, what does this mean? which means this. You know, the area under this function is equal to 1.0, right? 0.6 means at some g, the area until that value is equal to 0.067. That's the meaning of the CDF, right? Okay. So, you know, in the mean, we expected this is mean value is the 10,000 and standard deviation is 1,000. So this one sigma location will be 11,000, 12,000, and the like, and 9,000, 8,000, and the like, right? Okay, what would be the probability of this demand turns out to be this 11,000? Well, we can read that y-axis and guess that the probability is something, something, something. The reason why you use this, the large g function, is now we are interested in what would be the probability of having g value less than something. In our model, that's important. Okay, so that is g value. But I think this sign may confuse you, but this is nothing more than just a normalized normal distribution. G is actually your normal distribution variable, which is Q minus mean value divided by that. You know, there are infinite number of normal distribution. As long as it follows this bell shape, it's a normal distribution. In that case, we cannot pre-calculate any tables or something like that. So what we did is we normalized it. Because of this nice function, we can shift those mean value to 0, and we can scale those standard deviation into 1 by this transformation. Okay? So whatever it is, whatever the value of this mu and sigma is, we can normalize it with this transformation, and we can read those exact value at the normalized normal distribution CDF table. It's just mathematics. Okay, question? Okay. This is the most important thing. You've got to think about it, because unlike the model we've talked so far, it is not directly dealing with the cost itself. It's a probability. Okay? And the reasoning behind of it is what? We've calculated the cost with C average times average unit plus C shortage times shortage unit. You know, in reality, our inventory cannot be both in short or in overage at the same time. If the inventory is less than the demand, then we are in short, and that's it. Vice versa, if the demand is less than what our inventory, it's overage, and that's it. There is no overage and shortage at the same time. But what we did is we assumed that cost and CO times number of overage plus CS times number of shortage. Virtually this is impossible. However, what we did, because we set the expected value operator here, expected value over here, because the demand is random variable. Okay? And we derive the the total cost function in integral form, and in the integral form there is a probability function of this demand. So we are dealing with probability. It's exactly like, you know, lottery or something like that. You know, do you know what I mean? There is it's a probability of happening some case, and the benefit out of that case can be calculated and multiplied and summarized. Then we can calculate overall expected revenue from a lottery or something like that, and it is always less than the lottery actual lottery ticket cost, right? We did the same thing. Okay, questions so far? Yep.
Don't we have to actually find out the value of this from the crowd distribution table?
This C, yes.
When we are finding, actually, it will be needing a level of significance. Because I have seen the tables, all of they have level of significance.
What do you mean by level of significance?
The percentage that the probability can be satisfied. Like if 5% level of significance, the probability of error and probability of not error.
Okay.
Total confidence.
Okay.
You haven't really mentioned it here.
Mm-hmm.
Because I think all the statistics table actually contain a certain level of significance.
Okay, I think that's a very good observation. However, if we are allowed to use some, MATLAB or some very nice tools, we don't have to follow all of this. This value just can be calculated by calling some function, right? And it means probability. Okay. 67% of probability is the optima. The model is giving this information, this exact information. 67% probability. What does that mean?
The probability of finding that value.
Yeah, let's go back to the definition of this large G function. It's a probability of X is less than demand, right? We don't know exact demand. All we know is this demand is following normal distribution with mean value of 10,000 and standard deviation of 1,000. It could follow another Weibull, beta, or whatever distribution. But anyway, based on some marketing or forecasting result, assume that this is normal distribution, since normal distribution is the easiest distribution to manipulate. Okay, but anyway, it's a random. It could be a million. but with very, very low possibility, right? And it's this is G, small x, which means the set value. Okay? We use this Q star, which means Q star. What's a Q star? Optimal inventory size. So, optimal inventory size is, the demand is less than the optimal inventory size is 2/3. That's the optimal. That's the basic information what this model is giving to us. So, if the demand is over our inventory size, could be if the demand is less than our inventory size, could be, but which one is higher probability? Demand is less than our inventory size has the 67%. If you look at the other way, is the probability of demand is greater than our optimal size is 1/3, right? Yeah. That's the basic information. Yeah. Okay. Let's discuss about this model a little bit more. If this is a normal distribution like this, we are determining Q star, which one? And in current example, our specific Q star is around here, and where the area here is 67% and area here is 33%. Okay, that's the calculation of that. Okay, when Q star is higher than mean value, which means this one. If this is greater than 0.5, at the mean, this is half and this is half. So if we choose the mean, then this is 0.5. If this value is less than half, the value will be around here. If it's greater than 0.5, the value will be around here. So the important thing is, if this is greater than 0.5, then we know that the probability will guide us that the optimal sizing is around here, which means this one means when Q star increase, then function value probability density actually this decrease, which means I'd like to talk about the sensitivity. When the arrow is playing around here, it's playing around here. It's less, the variability here is less than variability here because the slope is like this. But when it comes to this area, the variability here is much, the variability here is much greater than variability here because the slope. Okay? That's the observation from mathematics, right? And what does this fact give us in terms of inventory control? Okay, let me ask this. What is this? This means CS is actually half of the, 2, and most of the time this means CO is equal to CS. Cost of overage is equal to cost of shortage. Okay, so overage and shortage does not make any differences. Okay? What is this in our case? Which means CS is much greater than CO, like this. CO is $0.50, CS is $1. CS is shortage are much more important in this case. Shortage is major player, and this is overage. Overage is most important thing in this case. Okay? Which means, let's think about this one first. The sensitivity about Z value, which directly relates to the size of the optimal inventory. The variability in inventory does not make much of the differences in this area. Which means, which means okay, think of the variability. We are all dealing with variability, and we don't like variability at all, but real life is full of variability. Demand variability. Well, that's too great, so we assume that this is the random variable, right? If the variability is higher, in this case, then what? It's related right there. And any observation about this fact?
The variability in demand will be demand will be higher and cater for it.
Demand will be higher in case of shortage. Right. In more precise term, the variability in demand is higher, right? vice versa here. So, does that make sense? Changing variability in this axis is variability in inventory size, right? Because G is related like that. And what does this variability in y-axis means? The probability of having what? Okay, I said this. And this region we call this is shortage region. This is overage region. Okay, another term. Variability is actually, this is normal variable, but with same mean value. This is normal variable. What the variability is defined? It's all about standard deviation. With very small standard deviation, it will behave something like this, right? This is, let's say this is A and this is B. Which one has higher variability? Yeah? B? A. Let's say this is C. Which one is higher variability? Right. If the normal bell shape is spread, the variability becomes very, very large, right? Which means those one has higher standard deviation, right? Okay. Okay. So it's a standard deviation of our random demand X. If variability is increasing, then in this region, Q is increasing, and in this overage region, Q is decreasing. Does that make sense? Okay. Okay, let's think of the base stock model. This is another model. In the EOQ model, we assume that delivery is immediate, and this is just for the simplicity purpose. But in real life, when you order some part, it takes many times. That's more realistic, and this model is dealing with specifically that part, which means manufacturer or vendor of our part is slow to fill our replenishment order. then, for example, we are assembling something and sell our final product, and we need some part, raw material. And if our inventory level of the raw material is very low, we put replenishment order to our supplier, right? But think about when this delivery time, when the time between you put order and the inventories comes into your factory, those time is relatively very long. Then thing is like this: we got to keep a safe stock, which prevents us stop working because we don't have enough part to work on, right? Then if they are very slow, ourselves, the store, must carry some stocks in order to meet the customer demands promptly. And the thing is, we'd like to determine how much stock. Okay? Let's begin with assumptions. Anyway, did you get the idea what kind of this model is? There is some safe stock level. Even though we have plenty of stock left, but at that safe stock level, we got to put a reorder, replenishment order to our supplier because they are very slow to fill our order. Delivery is not instant. While waiting for that orders to be delivered, we have to use our safe stock level to meet the customer demand because customer demands are just happening continuously, right? Assumption. No interaction assumption, which means product can be analyzed individually this is very strong one, which means we are going to think about that our factory or store only sell one type of product, no interaction. And demands occur one at a time, which means like this. If we are selling a TV, all customer demands are one by one. One demand, and one demand. Nobody comes to us and asks, I will buy 12 dozen TV set at the same time or something like that. Unfilled demand is back ordered. A back order is quite common in United States. This is like this. Think about you are a customer and there is one TV store. You go to that TV store to purchase one TV set, but at that time the store doesn't have any TV set left. So what you do is, I will pre-order my TV set. So when the TV set is delivered to your store, then I will buy that TV set. It's the same thing. Back order. Okay? Okay. Even though this replenishment time, lead time is very long, even though this time is very long, we just assume these times are fixed and constant. Constant means too strong assumption. Are known. Also, replenishment are ordered one at a time. That's the assumption. So, by these assumptions, you can sense that this is a product like some bulky and, bulky and some expensive and take some time to order, or such kind of product inventory control, like a TV set or a refrigerator or cars or something like that. If the basic application area is replenishment time is really, really, really long. And in most of the case, they purchase one by one and they order one by one. And you can guess there are many products which can be explained in this characteristic. This model is all about those inventory control. Okay. Before we derive the formula, let's write some mathematical notation. Let's say L is the replenishment lead time. Well, it's going to be some time unit. So let's say this is in just days. X is demand. Not the normal demand, but the demand, demand requires some time units. Annual demand or monthly demand or something like that. This demand is demand during L. For example, it's take about 15 days to get the replenishment order of some TV set. Then X is what is the demand during these 15 days. Okay? And as we assume, this L is constant. And we are not relieving we are not going back to the more simpler model anymore, since we relieved that demand is a random variable. In this model, demand is also random variable. And also small px is large p, large x equal to small x, which means probability demand during replenishment, lead time equal X. Okay, in previous model, we assumed that CDF, some demand is less than some value, those probability. But this is not that kind of thing, because it's not about area, it's just about that probability. It's a probability mass function. And we have the same thing here, large Gx okay. This is probability during replenishment lead time L is less than or equal to X. This is CDF. Be very careful about this English. It's a probability of this. Okay? This same thing here. And some much more thing. Theta is expected value of the random variable X. Mean demand during L. Sigma is standard deviation of demand during L. H is cost to carry 1 unit of inventory for some time unit, for a year or something. So unit is in dollar per unit per year. B is cost to carry 1 unit of back order. Inventory, you guys have to be very careful about this inventory and back order. Inventory is the things I currently have in my stock, but back order is some kind of future inventory. I ordered it and it will soon arrive, right? For a year, same unit. R is reorder point. In unit. This is when to order. When this means that when our inventory level, number of unit in my inventory getting low and low and low and eventually becomes to this R, then I will put reorder, replenishment order. And we'd like to determine this safe stock level. So this is going to be our decision variable. Because how much is stock? So if I explain this one a little bit more, it's an inventory level which triggers the replenishment order. Okay. Something more. R is defined as base stock level, also in unit, and small s is defined as safety stock level, also in unit. I know there are lots of new concepts and terminologies coming in, but everything will be explained later. And large R fill rate which is defined as fraction of orders filled from stock. And large BR is average number of outstanding backorder. And large IR is average on-hand inventory level. All these three are the function of base stock level. Okay. As I mentioned before, backorder is a kind of inventory. But in order to differentiate this backorder from real inventory, I put this on-hand inventory. On-hand inventory means the real number of units right at your store. Okay? So, inventory is it's an on-hand inventory minus backorder plus orders. Okay, let me explain it later because anyway, let's summarize it. This is about base stock, and we'd like to decide how much stock to carry, what's the optimal stock level, and we'd like to determine this small r with respect to all these large R and S, base stock level and safety stock level, and I will explain those concepts of these stocks in next class. But anyway, this base stock model is nothing more than just a little expansion of this Nussbander model, calculating all the cost. But this cost calculation, we have to think of the probability as we do in base Nussbander model derivation. But assumption is a little bit different, so approach should be a little bit different. But don't be scared. It's just nothing more than relieving some of the assumptions and continuation of our inventory model. Okay, thank you. One more thing. Are you familiar with the Poisson probability function? Poisson? Not the Poisson ratio, Poisson distribution. No, you're supposed to. So, in derivation of Bayes-Stokes model, we have to touch a little bit about this Poisson probability. So, review some of your old mathematics book and prepare it. Okay, thank you.